Welcome to this lecture on the Lotka-Volterra competition model. In nature, survival is rarely a solitary game. Today, we are going to explore the fascinating mathematics behind what happens when two different species are forced to compete for the exact same limited resources. By the end of this session, you will understand how ecologists predict whether these species will peacefully coexist or if one will drive the other to extinction. To understand this model, let us start with a simple analogy. Imagine you are opening a small coffee shop in a neighborhood that already has a popular bakery. Both of you are trying to attract the exact same group of morning commuters. If you were the only shop in town, your business would grow until you reached maximum capacity. However, because the bakery is there, every customer they serve is one less customer for you. In nature, animals and plants face this exact same struggle when they share limited resources like food, water, or space. This model predicts who wins that battle. Now that we have our analogy, let us look at the ecological foundation. The Lotka-Volterra competition model is built directly upon the classic logistic growth equation, which normally describes how a single population grows until it hits its carrying capacity. To account for competition, this model introduces a special multiplier called a competition coefficient. This is crucial because it translates the physical impact of one species into the equivalent impact on the other species. By doing this, the model mathematically links the population growth rate of the first species to the population size of the second species, and vice versa. Building on that foundation, let us examine the specific equation that governs the growth of the first species. The fraction on the left represents the rate of population growth over time. On the right, R1 is the intrinsic growth rate, telling us how fast the species would grow with unlimited resources. K1 is the carrying capacity, the absolute maximum number of individuals the environment can support. The most important new piece is alpha, the competition coefficient. It represents the effect of species 2 on species 1. When the population of species 2 increases, the available resources in the numerator shrink, causing the growth rate of species 1 to slow down. Just as we defined the growth for the first species, we have a perfectly mirroring equation for the competing species 2. Here, N2 is the population of species 2, R2 is its intrinsic growth rate, and K2 is its specific carrying capacity. The symbol beta is the competition coefficient, representing the effect of species 1 on species 2. If beta is a very large number, it means even a few individuals of species 1 will severely reduce the available resources and stunt the growth of species 2. Again, as either population increases, the available resources shrink, slowing down growth. Before we move on, let us see this with a concrete example. Imagine a forest with native red squirrels as species 1 and introduced gray squirrels as species 2. We are given an intrinsic growth rate of 0.5, a carrying capacity of 140, red squirrels, 20 gray squirrels, and an alpha of 2.0. We plug these into our formula. First, we calculate the competitive impact. 2 times 20 means the gray squirrels consume resources equivalent to 40 red squirrels. Subtracting the existing squirrels and this competitive impact from the carrying capacity leaves very little room to expand. Solving the math gives us a final growth rate of 4 red squirrels per year. Physically, this shows how heavy competition severely stunts population expansion.
Now that we have calculated a growth rate, we must understand the broader implications of these numbers. This mathematical model is absolutely critical because it forms the basis for Gauss's competitive exclusion principle. This principle states that two species competing for the exact same resources cannot stably coexist indefinitely. In the real world, conservation biologists use these very equations to predict what will happen when an invasive species, like a non-native fish, is introduced into a vulnerable lake. Without this model, wildlife managers would have to rely entirely on trial and error, which could lead to irreversible ecological disasters and the tragic loss of endangered native species. Understanding that competition can drive a species to extinction leads us to an important question. At what exact point does a population completely stop growing? Ecologists call this tipping point the zero growth isocline. A population stops growing when its growth rate is equal to exactly zero. Looking back at our Lotka-Volterra equation, this stagnation happens when the term inside the parentheses equals zero, which physically means the environment is completely full and absolutely no resources are left. Finding this line helps us determine the exact balance of populations required to halt growth entirely. So we know the concept of the zero growth isocline, but let us prove how we find it mathematically. We start by setting the entire population growth rate equation for species 1 to 0. Since the intrinsic growth rate and the current population size are not zero, the fraction representing available resources must be the part that equals 0. Therefore, we can simply set the numerator of that fraction to 0. This gives us the equation k1 minus n1 minus alpha n2 equals 0. This mathematical reasoning establishes that the carrying capacity is completely used up by the combination of both species. Now, let us apply this derived equation to our specific forest scenario to find the final result. We substitute our known values, a carrying capacity of 100, an alpha of 2.0, and a current red squirrel population of 50. We leave N2 as our unknown variable to find out exactly how many gray squirrels will push the growth rate to 0. Simplifying the numbers gives us 50 minus 2.0 N2 equals 0. Solving this simple algebra reveals that N2 equals 25. This proves that it only takes 25 gray squirrels to completely halt the growth of 50 red squirrels, demonstrating the severe power of a high competition coefficient. Having proven the math, let us look at how this translates visually. Here, you are seeing a zero growth isoclines graph. The horizontal axis represents the population of species 1, and the vertical axis represents species 2. The two diagonal lines are the isoclines we just learned to calculate. The outer line is the isocline for species 1, connecting its carrying capacity on the x-axis to its competitive limit on the y-axis. The inner line belongs to species 2. The arrows represent the trajectory of population changes over time. Because the isocline for species 1 is entirely above species 2, the arrows ultimately point to the bottom right corner. This visually teaches us that species 1 will always outcompete species 2, leading to a stable equilibrium where species 1 wins and species 2 faces extinction. We have covered a lot of ground, so let us summarize the key takeaways. First, the Lotka-Volterra competition model is a powerful tool that reveals the hidden mechanics of species rivalry. Second, we learned that competition coefficients are the key to translating the physical presence of one species into the resource use equivalent of another. Finally, by calculating zero-growth isoclines, we can predict the ultimate fate of competing populations, whether that is peaceful coexistence or brutal competitive exclusion. You have now mastered the mathematical foundation of community ecology, proving that survival in nature is always a delicate balance.